Our next presentation is a bit of it's a single presentation, but it's a Matt Leach, Scott Miller initiative here, and Scott is going to make the presentation. But I want to just run over Dr. Matthew Leach's CV here because there's a line in it I like, and he's a professor of wood sciences and wood products at Lakehead. He received a Bachelor of Science in Forestry and a Master of Science in Forestry from the University of New Brunswick, and a PhD in 1999 from Melbourne in Australia. He spent a few years in Melbourne working there, and then came back to Canada in 2003 and took on his current position. His research is mainly about wood quality and value added, where he and his group have developed a whole tree property mapping system and have taken this to the landscape level. His other research involves bioenergy. Well, in my experience, you talk to Matt about something and he's interested, and he'll take on just about anything. But there's bioenergy, engineered wood products, wood chemistry, tree properties, portable milling, and providing a fee for services and consulting. He's kind of a widespread individual. The thing I like about his CV here says, Matt loves all things wood, is an enthusiastic woodworker, loves the outdoors, and of course, a glass of nice red wine. It doesn't that just add a touch? I think that's the Australian rub-over coming out in him. The presentation today is going to be given by Scott Miller. Scott today is working as a forest industry development advisor in MNR here in Thunder Bay. At least I think you're still in Thunder Bay. Yep, okay. He's also completing his PhD in forest science at Lakehead under Dr. Leach. And Scott's research focuses on the end-use prediction of standing timber and forest products optimization. In other words, how much is there? I think that's what it means. And how big is it? His master's research was focused on modeling the attributes of eastern larch grown in Ontario to predict end use, which was in partnership with MNR's Growth and Yield Program, eFRI, the Northern Biodiversity and Monitoring Unit, and Lakehead University Forest Products and Marketing Program. Talk about cooperative management. That's to the nth degree. Matt and Scott have accumulated quite a substantial data based on the forest resource attributes of northwestern Ontario tree species. And that's as far as I'm going to go here. Scott, it's all up to you. I hope the class is in tune here. Are they, guys? Do you know that? You don't know. Okay. We hope they've cut in, and they should be. And if you aren't, guys, you're going to catch it tomorrow. Scott, you're on.
Hello, I'm Scott Miller. I'm with MNRF Business Development Branch. I'm also completing my PhD at Lakehead. I'm doing a lifetime PhD. Most of the people on my original committee have retired. And it's not getting any better when I work for the MNRF. But this program that Forestry Futures Trust supported, it was really an operational demonstration of my PhD app. I created a wood science app with Matt Leach. And we're going to present how it started, tell you a story, and hopefully be able to do it all in half an hour. All right, so I'm going to do a summary of the research, development of the wood science app, further enhancements to the eFRI, and the Forestry Futures Trust project. So Lakehead University has the research goal of training highly qualified professionals and support sustainable forest communities, while Lakehead University Wood Science Testing Facility, which is where I have worked and that Matt is the director of. And then LUSU has the broad goal to identify new market opportunities for the region's forest sector using wood characteristics mapping, and the purpose is to assess whether wood characteristics mapping provide an opportunity to optimize the value chain. And so my master's, my PhD, and this project were all based on those goals and purpose. So this slide here basically is a 10-year-old slide, but it says it the best. If we don't keep doing research on potential wood products from our forest, then we will fall behind the rest of the world and not be able to sell our wood. Most of the things that were at the like for all the bio product stuff at the beginning of the chart is now at maturity in that 10 years. So this is really a graphic demonstration of we need to stay on top of things. This requires science-based understanding of the useful characteristics, limitations of wood supply, merchantable, unmerchantable, and unutilized. So again, we didn't focus just on merchantable wood, we focused on all wood, including residuals, what people left behind, unutilized wood like larch and eastern white cedar, and wanted to include that in the eFRI. General understanding of wood science is, I'm a professional forester. I took wood products in my undergrad and found out that I knew nothing about wood science. So we don't teach foresters wood science. We teach them that there's wood and this thing, we do wood identification, but we actually don't teach them wood science, which is unfortunate. At Lakehead, they have a stream, Forest Products and Marketing, where they do a focus on wood and what it means and how variable it is. So the first thing we have to understand is wood is not wood. It's very variable. It's variable within species. It's variable between sites. Most people that work with wood understand that, but our policies don't reflect that. So site variability in wood is huge, and anybody who kilns wood or tries to dry wood will be the first people to identify that. But wood density is the best property to understanding wood because it encompasses everything. You understand that it changes with moisture. It changes both on all axes. The drier the wood gets, the more brittle it gets. The wetter the wood gets, the least strength it has, and a sponge reflects that. Having said that, density is also is used as a general descriptor of wood, but it's actually variable within a species. And so from radially from pith to bark, and actually from bottom to top, it changes. And we love to do in wood science these generalizations that wood increases as you leave the pith and head to the bark. Well, that's actually not true in all species, and that's not true within species. So we needed to be able to capture these changes in wood properties within species and between species at a site level. And that's where our research and this wood mapping stem from. So this slide just reiterates that wood changes with cambial age. So that's actually and radially. And then it's tied to a number of design criteria that our end users, production manufacturers, architects look for. And so we can actually take the wood properties of a species and we can put an attribute to it, and we can actually remove species from the formula. You're looking for this attribute, we have this volume. And so the forensic characteristics of wood describe the distribution and variation of timber sources. Wood such as paper, cardboard, fiber retain the forensic. So that's the other thing, is that wood is the parent, and everything that uses that wood inherits the same properties. So if you use 5 different species, your end product is going to be so variable that it would be challenging to make the same product over and over again. So if you're an OSB manufacturer, you want to know where all the same type of wood is, or the similar wood, so that you can meter your feedstock. If you're a bioplant, same difference. You want to meter your feedstock to get to a result. And if you don't understand the variance across the landscape or within this tree, then you're challenged. So if we look at the Canadian Forest Service publishes the strengths and related properties of wood grown in Canada, and we see a trend that if it's a commercially interest species, there's way more sites have been and way more plots have been used across Canada, and if it's an underutilized species, there's very few. But the biggest thing is that this is the national averages for species in eastern Canada, and the sheer limit of the sample size was shocking. And then when you look at the species distribution on northwestern Ontario, and you look at what we do, ours is very similar. So if you want to know how many growth and yield plots in black spruce, this graph is representative. It's not exact, but there is a correlation between the sheer amount of black spruce on the landscape and how much we survey black spruce, and how much do we survey tamarack or black ash or black poplar. They're all viable species on the landscape. They all offer fiber for different opportunities, and they all have design attributes. And so we wanted to pick this stuff up. So again, age is not the difference, right? So this is two larch trees. One is 42 years age and one is 120, but they're the same diameter. So just giving someone a diameter without age is not helpful when you predict wood properties. Same thing with trees. Breast height for a tree growing in the James Bay lowland and breast height for a tree growing next to Lake Nipigon have two very different answers, but all of our wood properties in Canada are done at breast height. So they don't mean anything. They're just a number. So we put all that together and we created this wood property. So it's site-specific, stand-specific, species-specific, and then we started to partner with Growth and Yield, who taught us how to do the field work, because this was all lab work. So we did the destructive testing, and we basically would dissect a tree. And destructive testing is very costly, so this is why we don't do it that much in Canada. It takes like days and days and days to process a tree where you're labeling every single part of the tree. So you have a tree, you take it into bullets, you label it, you cut it into boards, you label it, you cut it into test specimens, you label it, and you hire a bunch of students and hope that they don't write down the measurements wrong. But what you get is this. And so this was produced by Growth and Yield for jack pine based on our research, and we actually now started to see density variation at the landscape level. But still, that's not giving you in-block variance, and that's not giving you within species variance. So how do I deal with the top of the jack pine? How do I deal with the bottom of the jack pine? So one of the factors we did notice, just like the last speaker pointed out, is we don't have slope. And for wood properties, slope is huge. Slope and moisture are your greatest predictor of variance within a species, and we don't have reliable slope in our eFRI. So that's a limitation to being able to predict wood properties from the eFRI. However, when you add slope, this is larch. So again, the same Growth and Yield made that map for us, but we can then go to each one of those and tell you how slope changed it. So larch is one of the most sensitive species in the boreal. Light and water affect it greatly, so a little bit of water has a big effect, and well-drained soil. So the best growing larch, or the biggest larch, grows on sand or feather moss, right? And it's actually a condition of oxygen. The more oxygen in the soil, the faster the tree loves it. So it doesn't need soil to grow is the big thing, it just needs water going over its roots. But if it floods, it dies, and if it has drought, it dies, and if a black spruce grows up next to it, it dies. So it's a very sensitive tree, and it's hard to replant. But slope, the point is the slope is like little steps affect that species. So then we took the mapping exercise, and we went to eFRI, and they used their Buck program and matched our methodology with just clear cutting and chipping, and we saw that by understanding the value within a tree for its properties, both axially and radially, we could increase the value from a harvesting operation by 31%. So again, that's all very nice, and it's theoretical, but we needed to have more field calibration with Growth and Yield. So we merged Growth and Yield's field methodology with our field methodology. So our field methodology included ASTM standards. And so we modified the ASTM standards to accommodate the Growth and Yield STEM analysis. And then Growth and Yield didn't like the fact that our students could, our field crews could write what they wanted. They wanted them to be able to validate the data in the field. So they provided the Far North app. So in other words, if you have a 1 meter diameter tree, the app says, no, that's impossible. You drop the decimal point. Where in our field notes, we would often have to go remeasure because the student's handwriting was bad, or they forgot to measure something, and their app wouldn't let you proceed unless you actually had all the measurements. And so this is actually why we went there, was because students were unreliable and Growth and Yield had a great app. So we surveyed for larch all over northwestern Ontario, and we did the methodology by ecoregion, so that we had a balanced sample set in ecoregion. And with the exception of the Fort Frances area, which has very little crown land, we put wherever there was a STEM analysis plot for us, there was a Growth and Yield plot for M&RF. And so we went with growth and yield crews all over the province, and we doubled the amount of surveying that we could do because we had 2 different crews doing the work. So we had a total of 475 sample trees from 185 plots with 176 destructive trees. So that took 3 years. So then we realized that, well, that's way too much work, so we need to be able to do non-destructive testing, and so we started experimenting with larger diameter cores and acoustic velocity, densitometers, all sorts of non-destructive forms of testing, and we were able to come up with the same results with less money and faster. And so the key is going to larger diameter cores, going to the 12 millimeter cores, because now instead of bringing back a bolt, all we had to do is bring back a core, and we could do almost all the same tests in the lab. And so this shows you the variance within a tree at the radial level. So it starts off with the pith, the juvenile transition, and all that. This is representing fiber length, but this correlates with density, this correlates with modulus of elasticity, and so that's how variable you can get in a stem. And so we can map that with acoustic velocity, and so we really like that. So instead of having to take a test stick 30 centimeters long, 2x2, we could use an acoustic probe, and we prevented that destructive testing step. And so again, like I said, all these test factors were correlated, so that allowed us to use that 12 millimeter core and the acoustic velocity. And so if you have acoustic velocity, which is the green, and I don't know how to use the pointer, but the green at the top, it's correlated with MOE and fiber length, fiber angle, and so we were in business. And so then we found that we could take our design criteria and we could put it into machine grades. We could do it for density categories, and we could eliminate the disconnect that I discussed earlier where stem measurements, ELC, all that data was collected. We'd put it into Excel, and then the intersects between all the data. So we have a representation of ELC for every data point in the tree, and Excel crashed because it was over 3 billion intersects. So this is another reason why we had to create our own app, because the growth and yield app was just the field measurements, and we were finding that when we took field measurements and tied them to wood property measurements, the intersects were too great, and we had to come up with a database that would handle it. So big data. So we have site, sample, so we're going the other way than what eFRI does. Instead of going from site to the whole province, we were going from a tree down to like thousands and thousands, hundreds of thousands of fibers. And how do you manage that, and how do you keep it moving? And so again, the Wood Science app was the answer, because as it points out, we were crashing Excel every time we merged all the data. So we developed the Wood Science app with FedNor, M&R, and Lakehead University funds. And the deliverables from M&R's perspective was complete specially explicit database and merge M&RF and Lakehead data, so they had been doing joint research for a while. So we were going to merge that data into the database and create a default reporting export functions. The commitment was to use NSERC Engage funding to work with local companies to further enhance the database, and work with Forestry Futures Trust to demonstrate the effectiveness of the app. So the Wood Science app standardizes tester forms with auto import functions. So if you, in the past, you would have to print out the tester form and then transfer it to Excel. Now it's done automatically. And if you're using any field equipment that has Bluetooth, it does that transfer automatically. So if you're using your hypsometer and it has Bluetooth, all your height measurements, all your diameter measurements instantly go into the app, and you're eliminating that error. Jordy's presentation with the backpack, that's what was envisioned. We worked with L.U. Karras, Alfred Renaissance Group, and we envisioned a LiDAR backpack with the glasses that do the measurements for you. They showed me a picture of it in one of the fairs in Vancouver, and that's exactly what the app is made for. All of the stuff is automatically uploaded to the app. It can do it now. It can even upload LiDAR. And then all of those measurements are all tied together, so that the association between wood properties and site and echo site is all correlated. So we have autofill functions for calculations. So there's a lot of methodologies for density correction, for wood property correction. So we don't need everybody to be a wood scientist. So we put those into the app and they're automatically corrected by region because it changes, right? We have different moistures, different temperatures. And so our app is regional. And when you start the app, you say where you are in the world, and then all the correction formulas automatically adjust. Auto functions for such things as wood property relative moisture and content of testing, and it also does a validation. So if the data is not statistic, if it's not normalized and it's not homogeneous, then flags go up, little red flags on all the data, and the operator then can check the validity of the data. Again, that was a growth and yield idea, and we ran with it. So this is our data. So like I said in the corner, it's regionalized. So that's the boreal forest. If you are in the Great Lakes and Lawrence in a hardwood forest, you would click that. If you were in BC, you would click the appropriate BC forest. So it was made so that it wasn't just for Ontario, it was for any region. Matt has research partnerships all over the world, and their research went into this lab, especially research from our partners in South Africa. So soils are really important, and you'll notice on the right side, we have drainage class because, again, we don't have topography, so our workaround was to say how rapidly does the water drain on the soil. And so all our data is three-dimensional, so when they're entering the site, they're entering the site where they were on the tree, where they were on the plot, where they were on the world. So all of our data can create a map and show you exactly where the tree was and where in the tree the sample came from. So it's all three-dimensional. And so custom research design is, because it was made by a university, so it's built for custom research. Project testing properties. We did prototype testing. We went to University of Minnesota Duluth and we created products. So we knew where the parent material came from for the products, and then we tested the products, and so we had a tie from where in Ontario did the material come from to make that product. So we made glulam, OSB, particle board, a variety of different products, and we could tell right from the tree the chain of custody to that product. And that was all. We couldn't have done that without this app. So we also can do 3D mapping, which is a real bonus. So not only is it a bonus in the field, so if they're in the field and they finish their measurements of the tree, they can pull up that tree and say, is the measurements right? And we actually had times where they had like a big growth in the middle of the tree because someone didn't do a decimal point, or they overrode the program because they were getting eaten alive by bugs, and we could immediately tell just from the picture that, no, that doesn't look like that tree. Like, you made a mistake. We can also partition the tree. So we can predict tree values by tree form because that's what this app does. It looks for these, the outcomes of the measurements and how does that relate to wood properties. And tree form is a huge one relative to age. So wood attributes from non-destructive testing, wood quality predictive model developed from destructive testing. So we did a whole bunch of destructive testing to produce the non-destructive testing correlation, and we put that in the app. And so this way it identifies the cream from the milk. So that's relative to a plant, right? Because wood quality is subjective. What's good wood quality for a stud plant is totally different wood quality for a pulp plant, totally different wood quality from, so the cream from the milk here is the attributes, the design attributes of the wood that was measured. And integrate product-specific wood quality labels into the forest inventory. And so this is the property track changes, and we've shown this to our friends in Finland, and this is the type of stuff they're already doing. So they're looking for, in their milling, to manage these attributes, and when it goes through their scanners and their acoustic evaluators, then it goes to the appropriate processing line. We're trying to do it before it even hits the logging truck, so you're sending it to the appropriate mill in the first place. So Finland and the European Union are doing this on the in-feed of their mills. We're trying to do it in the field. And so you can see from here, we got sapwood, heartwood, which have different properties depending on species, extractive values, moisture changes, all sorts of things. And then you have wood morphology, so mature wood, juvenile wood, and mature wood is stable and it's got nice fibrillar angle and it's good for drying, and sapwood is, in some species, is only appropriate for pulp or biomass. So, and then we can go, we use the small QMBA and large methodology growth and yield uses so that we can get a whole picture of the change within the site, and that was very helpful, and we saw very differences by diameter class and by height class, and so the app tracks that. And so in our methodology, you have to do so many large, so many small, so many QMBA, depending on species composition. And we worked with growth and yield and northern biodiversity and monitoring to tweak that, because at one point we were doing all the heights and diameters, and John Pardon from growth and yield said, "Are you insane?" And he was right. We integrated back the old data so this log on the side is a cedar data, and so we integrated it all, printed out all the reports, and sent it off to MNRF and gave them a copy of it. But the cool thing was, from their measurements, our 3D modeler modeled their trees. But because they didn't do the internal properties, all you got was the outside three-dimensional picture. But that was awesome, that it worked on the old data because the same methodology was used in both data collections. So then we started to work with a bunch of different industry. So this is Sumac, and they did ground LiDAR. And so our app is showing the position of the tree and what the internal properties do, and their ground LiDAR was actually like taking a picture. It was amazing, except when you get to the crown, it gets all fuzzy. And then we did worked with GFMI and CCS on tweaking the app. So this polygon is supposed to be one polygon under the eFRI, and when we went and did the ground verification, we found that there was actually 3 different polygons from a wood quality forest products perspective. And so that was with GFMI and CCS. And then we did road location with Reno Pokey, so he's one of the investigators in this, and he has a program called Transport, and he did his transport with CCS and GFMI, and so we tweaked that. So now you can go by product class, and you can say from biomass, what's the best mill to send it to, and it will tell you the costs, and it has all of the mills in Ontario that we got from MNRF, and so it'll automatically find a mill that needs biomass and tell you the delivered cost. And so that's another now element to our app. And then we worked with KBM on LiDAR, and Jilly actually is here, who worked with me. He's now with FP Innovations, and we saw, in our methodology using growth and yield, we did crown measurements, so we did crown width measurements so that we could separate crown, and we did correlations with KBM's LiDAR. And so the heights diameters were correlated. We had a little problem with the crown for them, because their first pass at LiDAR, they were having a hard time breaking out crown, but I understand since they're way better at that. But yeah, so it was awesome. And so we could actually, because we had already measured it, we found correlations with LiDAR so that you could predict wood properties. So once we start knowing more about site, and we have a better description of site and species and age, we actually don't have to go into the field every time. We can tell you it would be in this area. This is what you're looking at. And so then we work with FP Innovations. They were one of my partners in my master's and PhD, and we are an Optitech researcher. And so the 3D nature of our modeling fits well with their Optitech. So you can now virtually do an Optitech on a standing forest as opposed to giving them a data set from the log yard. So the limits. So eFRI was a new animal to us, and we started doing eFRI just before the Forestry Futures Trust. We had been with growth and yield worked really well because it had all the things we needed. It had age, height, diameter, it had defects, because that all affects wood property. So we looked into the history of eFRI, and I thought this was very timely. So the credibility of the management design, so too large scale, in other words, is the point. And where we're trying to look at stem differences within a stand, the eFRI is looking at the whole province and how does that relate to the stand. And so since 1986, we know that the scale of the eFRI is too large. If you're trying to do something to optimize the local stand conditions, you're not necessarily going to get the right answer from the eFRI. So I got this from Jordy, and I'm hoping this still happens, but elevation is cool. a key. And so this was the intention a year ago to get the elevation model into the eFRI, and I'm hoping that still happens. And so then we went to Forestry Futures Trust, and we had a couple of goals that we agreed to do, determine if we can expand the current data collection methodology into eFRI, because we had been in growth and yield, and to include wood property attributes and other forest resources, and we will determine whether the expanded field collection activities are operationally feasible. So after we got accepted, it was accepted with this caveat, that we had to prove that it was operationally feasible to allow a new decision support tool technology to enhance the forest resources. So it's great that we're doing all these extra measurements, but is it cost prohibitive? So we agreed to that, because I love a challenge. So we went to the Dog River Mattawan Forest. So Resolute has always been a supporter of my master's, PhD, and then this research. So I'm very thankful that they've allowed me to work within their forests. So we chose 104,960 hectare area at the bottom of the Dog River Mattawan Forest, 202,000 hectares of forest land, and we used standard forest units as our measure, and we did 1 transit line for every 2,000 hectares. So our transit lines, or our calibration plots, were random, so that's different from what normal eFRI does. There's no putting it by the road. It was randomly chosen. We stratified the whole forest to take out any plots that would require a helicopter or a boat, but all other plots in the dog were legitimate, and we had crews, 5 kilometers, 4 kilometers, my crews right there. So they had to actually walk 4 kilometers, and Matt actually just came back from the forest from digging their truck out of a path that they thought they could drive down. So yeah, unlike eFRI, you had to walk the distance. You had to do it randomly so that the results were scientifically based. And so here's what we're looking at, the planning field, and we divided it into an east and a west block, and the difference in treatments between the 2 blocks is one was a GFMI crew, so that was the east block, and the west block was a Lakehead crew. So we wanted to prove that any crew could use the app, not just students that were taught about it in wood science. And even the Lakehead crew had never used the app before. They were trained on just like the GFMI crews, and did they get the same time response in completing the eFRIs? Did they get, and the answer was yes, they did. In fact, the students were better because I guess they were more afraid of me, because the GFMI crews, it was just another day to them. And where I was trying to get numbers and do this and do that, they knew what they needed to do for eFRI, and the wood science part was just an added thought. So here's a usual calibration plot, and you're supposed to do 10 points, 4 trees, So you're supposed to do 10 sweeps, 4 diameters, 4 heights, 1 core, and 1 soils. So our methodology is 10 sweeps, 25% of the diameters of any species, 30% or more. Same thing with heights. At cores, there's 1 for every species and 3 QMBA large and small for the lead species, and 1 soil pit. And then we did another one where we did what I was telling you before, where we were measuring all of them, where John told us we were crazy. And so here's the type of stuff that you can do. So this is jack pine oven-dried density. So we can actually take the green density in the app, and it will tell you right there in the field, the oven-dried density would be this. And so if you're a trucker, that's going to tell you how much water you're going to be driving to the mill and what you're not going to get paid for. If you're an operational person, that's going to tell you how much kilning time you're going to need, right? So the answer's right at your fingertips. This is oven-dried density modulus of elasticity for jack pine. So now you're using the design criteria. This is thermal values. So for the Resolute's cogen plant, they can tell where the best thermal value wood is and what can be used for that. Fiber length for their pulp mill. All of the plots did fiber length. And then this is timber quality by stand structure, so mixed versus hardwood DOM versus softwood DOM mixed woods. And then you could even get a printout. You can ask for the query, and you can ask it for whatever category: green, oven dry, 12%, and whatever species, like what standard, whatever parameter you want, you can put in the query. And so then we did comparisons of volume for the 3 methods, who could do what. So we use growth and yields volume taper calculations, not Plonsky, for most of our calculations. We did a time study showing that, so on the far left is the current eFRI system, the medium one is our modified one that we did with growth and yield, and the far one is if you measure everything. So the far one, of course, is cost prohibitive. You can't possibly measure everything and put wood properties under the same budget, but with the middle one, yes, it's not that bad. You get so much extra information for a little bit more investment. And then this is something you can do. So this is a prediction of volume for jack pine using diameter within the dog forest, right? So you can do your own attribute modeling right from the app, and this is a product from the app. And so again, for us in the app, the limits of what we can do are the limits of the eFRI, and so working groups in this case is standard forest units. So if people don't classify the polygon into the right standard forest unit, then that skews our results. And we had that with upland cedar and lowland cedar. We actually didn't find any cedar. So really skewed the results on what's the density and wood properties of cedar. And so what our app tries to do is it takes the modeling, which is at the provincial level for eFRI, and it brings it down to the stand and even the stem level if required, and that's instant. So you can create localized models relative to the eFRI using our app. Thank you. So this leads to supply chain optimization, and I have a whole bunch of people to acknowledge, and like half of them are in the audience. So GFMI was our partner for enhancing the app, and FedNor and NSERC and all those guys paid for it, and I would like to thank all of you for your assistance and questions.
Rather than asking questions in this session, I would suggest that for those of you who have such, contact Scott and Matt Leach afterwards here, and we're heading in the home stretch right now, and I don't want to run out of any more.
Sure.
Scott, excellent.
Thank you.
Okay. It has sure come a long way since we last saw it.
Thank you.